Now we're going to take a closer look at the microbial reactions that occur in wetland soils. The incredible diversity of chemical reactions that microbes perform in wetlands is one of the main things that makes wetlands unique. Most of these metabolic reactions evolved over 2 billion years ago, before Earth's atmosphere had been oxidized by green plant photosynthesis. Wetland microbes help remove nutrient pollution, provide sources of carbon to downstream ecosystems, and even control how bad the wetland smells. This stuff is why I'm a wetland ecologist. So let's have some fun. Wetlands are zones of intense biogeochemical activity. Flow of water and alternation of saturated and unsaturated conditions due to things like tidal flushing and saturation and drying following a rainstorm event lead to variation in oxygen and gradients of oxygen within wetland soils. Wetlands also receive inputs of different substances from seawater, from surface runoff, from groundwater, and from precipitation. And these things, these variation in oxygen and inputs of different substances interact to cause a wide range of biogeochemical reactions. Before we dive into specific processes, it's important to understand that these microbes are performing redox reactions. They're moving electrons around between different molecules and getting energy out of these reactions. Some microbes use this energy to fix atmospheric carbon into organic carbon, just like plants do in photosynthesis. These microbes are chemoautotrophs because they're using chemical energy to fix their own carbon. Some use redox reactions to burn organic material and use that for energy, just like we do. Those are chemoheterotrophs, just like we are. Regardless, all redox reactions involve an electron donor or a reducing agent and an electron acceptor or an oxidizing agent. If the reaction releases energy, then the reaction is favored. These simple principles explain the patterns in nutrient concentrations and microbial communities that we observe over space and time. Here's an example of a redox reaction that we're all performing right now: aerobic respiration. So earlier today, I had some tacos, and right now I'm using the oxygen in this room to burn those tacos and give me enough energy to talk about redox reactions. So in this reaction, aerobic respiration, oxygen is the electron acceptor. And the organic carbon from my tacos, or whatever you had for your most recent meal, is the electron donor. Oxygen starts out at a valence state of 0 because the electrons are shared equally between the two oxygen atoms. Carbon also starts out at a valence state of 0 because the charge in the organic carbon molecule is shared equally between the hydrogen and the oxygen, also in that molecule. The carbon is oxidized to CO2, or carbon dioxide, during respiration. The carbon donates 4 electrons to the oxygen atoms, ending with a valence state of +4. Each oxygen atom accepts 2 electrons, ending with a valence state of -2. The valence state of the oxygen and hydrogen atoms in the water molecule remain unchanged. So water is just a byproduct of this reaction. It doesn't really participate. Once again, carbon has donated electrons, ending with a more positive or less negative valence state. And oxygen has accepted electrons, ending with a more negative valence state. At the risk of belaboring this, these half reactions are another way to look at the redox reaction that is aerobic respiration. So again, organic carbon is the electron donor. It donates 4 electrons, beginning with a valence state of 0 and ending at a valence state of +4 or +4. Oxygen in diatomic oxygen accepts the 4 electrons, with each oxygen atom beginning at a valence state of 0 and ending at a valence state of -2. The sum delta G for this reaction is negative, indicating that the reaction releases energy. And it turns out that aerobic respiration releases more energy than any other form of metabolism. Oxygen, unsurprisingly, is the strongest oxidizer or electron acceptor that's available. It turns out that organic carbon is not the only electron donor. Oxygen will accept electrons from a number of reduced substances. The oxidation of these reduced substances releases energy, which often provides the basis of chemosynthesis, or taking inorganic carbon and fixing it into organic carbon. Other electron donors can include substances containing hydrogen. When microbes oxidize ammonium to nitrate, this process is called nitrification. This is a form of chemosynthesis. When hydrogen is present in an oxidized environment, it will react with oxygen spontaneously, and this is called an explosion. Hydrogen is a great reducer. It's a little too great. It releases too much energy. It would form the basis of a great metabolic reaction, except for the organism performing that reaction would explode. So you don't tend to see that. However, when microbes oxidize methane to form CO2 or organic matter, this is called methanotrophy. And again, that's a form of chemosynthesis. Microbes will also oxidize reduced metals when oxygen is available. And again, many of these reactions form the basis of chemosynthesis. In both cases, the reduced metals donate electrons, ending at a more positive valence state. And oxygen must be present in the soil in order for any of these reactions to occur. Just as organic carbon is not the only electron donor, oxygen is not the only electron acceptor. And this is where things can get really interesting. Because in environments where oxygen is absent or where oxygen runs out, like in the saturated soils of wetlands, other substances can replace oxygen in respiration. These can include other substances that also contain oxygen, like nitrate, sulfate, and carbon dioxide. When microbes use nitrate instead of oxygen to burn organic carbon, this process is called denitrification because it removes nitrate. When they use sulfate, that process is called sulfate reduction. This process produces hydrogen sulfide, or the stuff that smells like rotten eggs. This is why anaerobic or anoxic soils often smell bad. When they use carbon dioxide, they produce methane in a process called methanogenesis, because chemists are not terribly creative. Microbes can also oxidize reduced metals and use the energy from those reactions to burn organic carbon. In fermentation reactions, microbes move electrons between carbon atoms in the same molecule. In the first example, microbes move electrons between the 2 carbon atoms in acetic acid. The carbon that donates electrons is oxidized to CO2, and the carbon that accepts electrons is reduced to methane. In the second example, electrons are moved between 2 carbon atoms in lactic acid to form ethanol and carbon dioxide. Now, these reactions follow a predictable pattern depending on the amount of energy that is released from the reaction. As I mentioned earlier, aerobic respiration yields the most energy. So when oxygen is present, microbes that use it tend to outcompete other microbes and grow faster and form a larger component of the microbial community. When oxygen is depleted, microbes that can use the next most energetic electron acceptor, in this case nitrate, are capable of the most growth. and so on, with the microbial community next shifting to the oxidized metals, and then sulfate, and then finally CO2. If they run out of everything else as a last resort, they'll use CO2 as an electron acceptor. The redox potential of the environment determines which chemical reactions are favored within that environment. In oxidized soils, oxygen is typically used. In moderately reduced soil, typically nitrate. In reduced soils, even lower energy electron acceptors like iron. And in highly reduced soils, the lowest energy electron acceptors like sulfate and carbon dioxide. Assuming that electron acceptors tend to be replenished near the surface from the oxygen-rich atmosphere or from surface water, redox potential tends to decrease with depth from the surface to deeper depths in saturated soils. The most energy-yielding electron acceptors are used up first, and then the community switches to the next most energy-yielding, and so on. This means that microbial reactions also follow a predictable depth sequence in the soil profile, with aerobic respiration near the surface, then denitrification, and then metal reduction, then sulfate reduction, and finally methanogenesis. And you can find clues to some of these in the field. Iron reduction is marked by a transition from reddish-brown soils containing oxidized iron or rust to more grayish soils containing reduced iron. Sulfate reduction, as I said earlier, produces hydrogen sulfide, which smells like rotten eggs. So you can definitely tell when you reach that layer of the soil profile. So we've seen that the loss of electron acceptors follows a predictable pattern based on how much energy microbes can get from using them. But the availability of electron acceptors to start with depends on the source of the water that's coming into the wetland. Groundwater and surface water typically contain electron acceptors. As water passes across and through the land's surface, it picks up material from the soil. This can include naturally occurring metals or materials like nitrate that come from biological activity in the landscape. Wetlands that receive most of their water from precipitation are basically receiving distilled water. It will contain materials from the atmosphere like oxygen and especially carbon dioxide, but not much else. This water also tends to be more acidic, as the water reacts with carbon dioxide to form carbonic acid, and it can actually strip other materials from the soil over time. Tidal wetlands typically have an abundance of electron acceptors. Estuaries receive water from rivers, which pick up materials from the watershed, and they receive water from seawater, which is very rich in salts and sulfate. As I mentioned when discussing soil carbon storage, ombrotrophic bogs are a special case and tend to have very low rates of decomposition. The name ombro kind of gives you a clue as to how these bogs function. Ombro means sky, and trophic means fed. So ombrotrophic bogs are sky-fed bogs. In other words, they receive all of their water from precipitation. As a result, microbes in bogs have very few electron acceptors available to them. Basically, oxygen, which runs out immediately, and carbon dioxide, which releases very little energy when they use it as an electron acceptor. So microbes receive very little energy from burning organic carbon, and this results in extremely low rates of decomposition. Bogs also tend to be nutrient limited, acidic, and cold, and these factors also limit rates of decomposition. And these extremely slow rates of decomposition lead to incredible accumulations of organic matter, including these meters of organic matter you can see in this peat bog at the top of the slide, but also bog mummies. So most of us know that we find mummies in deserts because it's so dry that the organic matter does not break down. And it turns out that bog mummies are even more well preserved than desert mummies. So when this guy on the bottom of the slide, he was named Tulland Man, was discovered in a bog in Denmark in 1950, the people who found him thought that he was the victim of a recent murder, and they called the local police. The police showed up on the scene and said, "We don't think you need us, we think you need to call a museum because this isn't recent." And using C14 dating, researchers were able to date this guy to between 375 and 210 BCE. So he was over 2,200 years old. And he was perfectly preserved, except for his bones, which had dissolved. And they were able to determine, because he was so well preserved, his cause of death, which was strangulation, his last meal, which was a porridge containing barley and flaxseed. And based on that, they were able to put his death sometime during the winter because of the material that was in his stomach. They were also able to obtain a fingerprint because his hands and his skin were so well preserved, which I believe is still the oldest fingerprint still on record.